All right, everybody. So what we're going to do is this is the Monday, what is this? November, oh boy, 2nd, I guess. November 2nd, where we're looking at the velocity selector activity in mass separation. Some ideas around that. So here we go. So first up, make sure you have a pivot, interactive count. Second, Friday Madness, that activity with 3 problems. If you have questions, please reach out. Lastly, the hyperdoc. Make sure you're checking that regularly. So today we're going to focus on completing right-hand rules and applying it to a unique situation. So what we're going to do is we're going to start with a quick review. So if I have 2 plates, remember, whenever we get to a problem, try pausing it, kind of digest what's going on, and then hit play again. So I've got plates here, and we're going to be using them and thinking about what's going on. So first question is, draw the electric field. Electric field goes from positive to negative. It is the direction of force on a positive charge. Now, this problem, we're going to deal with an electron. So which way does the electron feel a force? Feels a force upwards. So there's an electric force up. Now, if that was the only thing that acted on it, it would go upwards like a parabola. It will not be a circle. It is not a magnetic force, but instead it'll be a parabola. So now, the question we have is, well, let's say you wanted to have it go in a straight line. Well, one option is just remove the plates. Why are they there? Okay, but the second is, well, could I put a second force on it? So the idea is really, well, if it's getting pushed upwards, well, what if I pushed it downwards with something? Well, gravity's not going to be strong enough for small charges. So instead, we're going to use a magnetic force pointed downwards. How we do that is kind of the guts of today. So we're going to be looking at that. Second thing is, what are we doing this for? The end product of this thought process is we're going to be able to choose the velocity of things that go into an experiment. And this is a really amazing tool to do that. All right, so here we go. Draw the direction in which the magnetic force must act. Well, if an electron is going this way, that means the charge is this way. And here's another reason. I was working with some people, and I think this might help. Since electrons are negative, I end up getting a current that's negative. So if I'm like, oh, it's going that way, well, the current is the opposite direction. Okay, so you take your right hand out. So if it's moving to the left, so it's moving to the right. That means my current is to the left. If my current is to the left, and I want, just like on that last slide, I have an electric force up, but I want a magnetic force. So B stands for magnetic. So it's going, the current's to the left. I want a force down. If you look, your thumb is down and your fingers are going into the page. So away from you. So my fingers here are going away. They're not going towards, they're going away. So my force is down, my current is to the left, and my field is going in. So I'm going to draw that. So that means my field is going into the page. So I have a magnetic field going into the page, but if I do that, I can get it just right, and it'll go straight down the path. Okay, so let's clear this out. Let's do a little mathematics review. So electric force is EQ. Magnetic force is BQV. And if I wanted to go straight down the middle, my acceleration would be, my acceleration would be 0. Yes, that's the correct answer. Which means the electric and the magnetic are in opposite directions, but equal in size. Well, that means I could say this statement. I could say the electric force equals the magnetic force. Let's write out what we got. EQ equals BQV. Again, remember, stop and pause. In case I'm going too fast in class, we did that a lot. We digested it. We asked questions. So do the same. So if I want to solve this for velocity, I would get EQ over BQ. My Q's cancel. That means the charge doesn't matter. It can be a big charge, it can be a small charge, doesn't matter. The only thing that matters is velocity. So if I wanted something to go straight down a path, I would have to balance this E and B. Well, E is balanced by electric plates, pluses and minuses. And my B field is either from a solid magnet that stays, or I could use electricity and have a coil of wire, which creates a magnetic field. So either of those. So anything that comes out will have, so let's do a quick example. Let's say your electric field is 100 newtons per coulomb. And let's say your B field is a really, really strong magnet of 2 Teslas. Well, if I do E over B, so I shoot a whole bunch of charges between these things, okay? The only ones that will go in a straight line are the ones that are at 50 meters per second. So anything that comes straight out of that, so let's say I had like a little spot for them to come out. Anything that comes out of it, I know its exact velocity. Pretty powerful, because now you know its velocity. You don't know its masses, you don't know its charges, but you know exactly how fast it's going. Okay, so now I have that written down too on the next slide. Look, same result. And so the idea of the velocity selector is if you have a whole bunch of charges going at a whole bunch of different speeds, because they all got sped up differently, as they go into this, the ones that come straight through have the exact velocity that is equal to E divided by B. Anything that's not that will go up or will go down. Okay. The link, I have these 2 links. One is a static website explaining what we just went through, and also another YouTube video of somebody else doing it. They're right-hand rules. They have slightly different conventions than we do. We do it this way: force, current, field. Theirs are slightly different. So just know that difference is happening. I'm going to show you this in an example in a second. So if they're going at just the right speed, they will take path B, go straight down the middle. Okay. An uncharged particle will also take path B, it'll go straight down the middle. That's an issue we'll deal with later, but the uncharged particle goes straight down the middle. Now the question is this. This is where it is. What if these particles are going too fast? Okay. So let's talk about this. The E, so I have a negative charge. I have it, and it'll be drawn upwards electrically. And it'll be pushed downwards magnetically. We're just going to write out our equations for these two, EQ and BQV. Which of these two, if I'm going too fast, will get bigger? This bottom equation will. It has velocity involved. Let's kind of highlight this. So if I were to make this velocity bigger, think about my equation, that'll make my force bigger. And if my force gets bigger, my arrow is going to get bigger. Well, which arrow has more of an impact? The downwards one. So it will go on path C. So if I'm going too fast, I will go down path C. Too slow? Pretty obvious. Just it's the opposite. Okay. And so which force remains constant? Your electric. Your magnetic changes. It is based off of the velocity. So if your velocity changes, your magnetic force changes. So that's really what we got going on. We also did positive. Let's get this, let's write this out. So positive, let's look at the forces. I'm going to stick a positive charge in here. Well, the positive charge will have an electric force downwards. Remember how this field is going in? Let's see which way the magnetic force is. Stick our right hand out. So positive is going to the right, so I point to the right. The field is going in. Which way is my thumb pointed? Upwards. My magnetic force is upwards. Look at that. If it's just the right balance, it'll still go down the middle. It'll still take path B. Those two will be the same. Uncharged particles and charged particles with exactly the right velocity will go in a straight line. But what happens if they're going too fast? Too fast, right? So too fast is BQV. If they're too fast, my velocity gets bigger, my force gets bigger, so my arrow is bigger. So which way does it go? Path A. Too slow, opposite. What stays the same? Electric. What doesn't? Magnetic. All right. Let's clear this goodness out of here. So this one here, There's a couple different ways to tackle this, but the idea is if it's going slow, that means the magnetic force has to be downwards. Because if V gets smaller, this arrow gets smaller, but my electric force will be bigger. It's not bigger because it's going faster, but it's that this guy is smaller because if it was too slow. Well, what type of charge would feel an upwards electric field? That would be a positive. Okay. So I'm going to open this guy up. So these are it's called a mass spectrometer and mass spec, just abbreviate it. But this link is a good one to tackle. So I'm just going to show you. So the first thing we do in a particle accelerator is we accelerate it. We speed it up. Now here's the thing. If things have different masses, they're going to speed up at different masses. They're going to have different final speeds. They have different charges. They're going to end up with different. So all of this stuff's going to leave this at different velocities. So then what do? We go into this middle piece, which is our velocity selector. So let's go into that. So if it's just the right speed, down the middle. But if it's going too fast or too slow, okay? So it's not going to end up through that. So a good example to think about is, well, what if you just had like a little brick wall here? Lead wall, preferably, right? And the only thing that could make it through this had exactly the right velocity. And you know what it is because you've controlled those two variables. Okay. Well, now remember, here's the problem. It gets into that. It leaves that, the velocity, but you don't know the mass, you don't know the charge. That's an issue. Which brings us to the third piece right here, which is a magnetic field. Just a magnetic field. And so when it enters that last one, there we go. When it enters that last one, look what happens. You have charges with known velocities. Remember how we had those neutrals? Well, neutrals don't do that. Neutrals would just go straight. But these guys, let's click that. But these guys, reset, right? If you have different masses, you're going to turn differently. So here's a review. This is called centripetal motion, mv squared over r. And that is caused by a magnetic force, which is B times Q times V. So if I set these guys equal, mv squared over r equals BQV. Isolate for the r, I get mv over BQ. So if you know what the B field is, and you know the velocity, because remember that velocity selector, you can measure the radius. So you now know that. All you have left with is mass and charge. Okay. Now, even if you just get mass to per unit charge, that's pretty good, because you might be able to accumulate some of this and know what its mass is with some experiments. And so there's some different strategies you have there. But you do get mass per unit charge. And this is what J.J. Thomson was credited finding as the mass per unit charge of an electron using this exact same setup. The more precise you are, the better your data is. Okay, so there's the catch, right? So let's walk through this. We then stopped and we said, okay, this first bit is going to give us information about, right? We have different potentials, different voltages. And then here I have my velocity selector. Okay, this is going to help me know velocities. And then when I get over here, if I have information about the charge, this is really going to help me with the mass piece. So if you have gases or materials and you're like, I don't know what it is, you can put it into this machine, run it, speed it up, see how it curves. And then from there, you can start to draw conclusions of, oh, it's this atom that I saw. So we did that in class. So now we're going to dive into the mathematics and just kind of take it one piece at a time. I'm going to get my face out of here. No need to write on paper. Well, we tried it. I made it so people had a room. So first thing we're going to do is we're going to determine velocity. Well, this is the velocity selector portion. So velocity. My experience is don't write V because we're going to talk about voltage in a second. So just write velocity is E over B. Now, look at what we got. We know what the B field is. They told it to us. It was 4 Teslas. That's kind of nice. But we don't know what the E field is. They gave us voltages. They gave us potentials. So the electric field is about the change in potential over a distance. So the electric field is change in potential. It goes from 1500 to negative 500, so it changes 2000 volts over 0.2 meters, which is 10,000 volts. Now, if I divide those, I get a velocity of 2,500 meters per second. So the only things that come out of this are either uncharged particles or objects that are going 2,500 meters per second. If they're not going that speed, they don't go in a straight line. They don't make it out. So let's do this here. So now let's write down a piece of information. We know the velocity, 2,500 meters per second. That's the velocity it enters this field right here. Now, it enters that field and it curves. That is a centripetal force. And it's caused by a magnet. So centripetal force is mv squared over r equals bqv. So if I solve that, I get radius equals mvu over bq. And this, I'm trying to find mass. So let's isolate for m. So we get m equals bqr over velocity. So my B field, this is actually a thing that people usually do is they'll accidentally use the wrong B field. So sometimes you'll have one B field in one area, one in another. And so my B field here is 2. Charge was given in the problem. It's kind of hiding, so I'll help you out. It's right up there. 4 times 10 to the negative 16, negative 16, times radius, 0.6, all over velocity, 2,500. Wow. Wish I had a calculator. Oh my goodness. Let's do this. 848. 4.8 times 10 to the negative 16 all over 2,500. Oh my goodness, Schmear. Let's see if I can do that. So I got 4.8 divided by 2,500. Let's see. Can we do 10 to that? Oh my gosh, I'm so sorry. Let's see standard. Let's see if I can do scientific. Oh, so 4.8 divided by 2,500 times 10 to the negative 16. Not minus, Schmear. Okay, so let's try it again. So 4.8 divided by 2,500 times 10 to the negative 10 to the that's huge. Okay, so I get a mass of 1.9 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 kilograms. That's not very big. Okay, 1.9 times 10 to the negative 19 kilograms. Determine the kinetic energy. Ooh, we could do that. So I'm going to clear this out just so we have some space. So 1.9 times 10 to the negative 19. So let's see, we've got our velocity is 2,500 meters per second. We have a mass of 1.9 times 10 to the negative 19 kilograms. So kinetic energy is equal to 1/2 mv squared. So 1/2. I think we've done that. If we haven't, send me an email. Schmear will stop everything. We'll have a quick refresher on that. But I think we've touched on it. So the mass is 1.9 times 10 to the negative 19. Velocity is 2,500. I get a kinetic energy. Oh, schmear. Okay, here we go. Here we go. So times 5 times 2,500 times 2,500. Oh boy. Here we go. 6. So the kinetic energy is 6 times 10 to the negative. Oh gosh, make me earn it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Huge. Okay. 6 times 10 to the negative 13. 6 times 10 to the negative 13. 6 times 10 to the negative 13. Okay, so now this next slot is blank. But here, 6 times 10 to the negative 13. So ready? 6. So the kinetic energy is 6 times 10 to the negative 13 joules. Now, that just tells me when this electron left, it was moving this way and it had that much energy. Well, look at this. How much energy did it have here? Nothing. But it was in a field. So now we got this is a good review. Energy in a field. So in a field, energy is equal to Q times delta V. Well, technically it's Q times V, but as we go through the field, we're going to change. Okay, so my charge is 4 times 10 to the negative 16 coulombs. That's my Q. Delta V, I don't know. It gave me one of them, but it didn't give me the other one. My delta U, it got this much energy. Well, where did that kinetic energy came from? It came from the field. So I can put it back into the field and say it came from the field. So I'm just going to deal with the tens first. Okay. So we got 6 times 10 to the negative 13 divided by 4 times 10 to the negative 16. So I got 6 divided by 4, which is 3 over 2, which is 1.5, times 10 to the third equals my delta V, which is 1,500 equals delta V. So my 1,500 volts. Well, it started at negative 100. So what does it end at? 1,500 volts higher. So V2 is at 1,400 volts. This is literally how they found the mass of an electron. But notice you got to do all the experiments to know what its charge is. So you have to get really creative with finding its charge. So these are things we can keep digging into. Let's see. Let's see if I have anything beyond the slide. That is it. So thanks for tuning in. Please ask questions. I have another AP Daily video that you're going to be watching, which is going to tackle and work with these ideas. And so the goal is to digest this and ask questions and grapple with it. This is a big idea. So tomorrow, one of the other things I want you to do is work with this app, play with it and go, okay, well, what happens when I have a bigger electric field, right? Okay, well, what does that do to my velocity? I'm going to have a bigger velocity. Okay, if I have a bigger velocity, what's going to happen? Well, how would I fix that? I could change the electric field in the B field. Okay, let's practice my right-hand rules. In this activity, is it a positive or negative charge? Like, these are all great kind of thought experiments you do as you grapple with it. Questions come out. So jump in, do the best you can, and let me know what questions I can answer. Guys, you're doing a great job. You are digesting high-level stuff, and you are really growing in your problem solving and your resilience. So don't stop. Don't give up. Okay? All right, guys. Talk to you later. Thanks for tuning in. Wash your hands. Be kind to each other.